Here's a quick refresher on state machines. A state machine is a general-purpose sequential circuit. Its hardware structure consists of three elements. The first is a memory device called the state register. This is a multi-bit memory normally composed of an array of D-type flip-flops. The particular pattern of ones and zeros inside the state register maintains the actual state of the machine. The circle denotes some combinational logic that's referred to as the next state decoder, or NSD for short. And this combinational logic examines both the inputs to the state machine, and we can have multiple lines coming in, as well as the present state of the machine. This would be the pattern of ones and zeros in the state register, again a multi-bit value. Considers both of those inputs, present state as well as the external inputs, and determines the next state to be applied to the state register. So again, next state is being calculated by these two values. We have the third element, which is also combinational logic, and this is called the output decoder. This accepts the state that's stored in the state register and determines which, if any, outputs to activate. So we can have multiple active outputs, one at a time, or none, depending on the needs of the state machine. This structure is referred to as a Moore machine. This is characterized by the outputs depending only on the present state. If we add a slight modification, we get the so-called Mealy machine. If we send the inputs all the way to the output decoder, completely bypassing the memory element, then we see that the outputs can depend both on the present state as well as the external inputs. And again, this defines the difference between Mealy and Moore type machine. Now the state register normally is connected directly to our system clock waveform. This would be a repetitive type waveform. And on each edge of that clock waveform, the state register updates its value, which is presented by the next state decoder. It also includes a reset input, and this forces the state register to an initial state. This is useful for the power on behavior, as well as bringing the state register to an initial state for testing. As I mentioned before, the pattern of bits stored in the state register defines the state, and we can refer to this as the state code. If the state register contains n flip-flops, then we have 2 to the n possible states. Now there's an alternative way of drawing this three-part structure, and this is more suited to the way we will implement a state machine in LabVIEW. I'm going to combine the next state decoder and the output decoder, which are both combinational circuits, into a single combinational circuit. And this single combinational circuit generates 2 primary outputs. One would be the next state, as I had up here, and then it also generates the outputs. Now this logic needs to look at the inputs as well as the present state. So we see that the inputs can be applied to both the next state decoder and the output decoder. Here's our feedback path. So again, we have the same circuit structure, just drawn slightly differently. Let's take a moment to consider the LabVIEW implementation. The state register is implemented by the feedback node So this portion would constitute our state register. This combinational circuit is implemented by the case structure right here. Again, that combines the next state and output decoders. Here we see our primary inputs, and for this example I'm just calling them A, B, and C. And the outputs of the machine would be the indicators called D through H. Here we see the feedback path. And as we look for other similarities here, the while loop implies the clock waveform. Each iteration of that loop constitutes one clock cycle. Now here we see a structure associated with the reset. Now the way this is normally thought of back here at the state register with flip-flops, this is normally connected to the asynchronous reset inputs on the flip-flops. In this case, we have a synchronous reset because I interrupt the output from the next state decoder to force a constant into the state register. Now it's important to realize that the inputs are sampled once each clock cycle. And that sampling effectively means that we have an additional register embedded between the external inputs and the combinational logic. And these registered inputs impose a one cycle delay. And it's important to realize that delay.